Okay, so this Google form here was from the Friday lab that y'all filled out. Um, Most grades were high 80s, if not 90s. I'll be logging those in. You guys will be seeing those before spring break. Um, but I want to take you through the questions that go along with the simulator lab on PhET physics through phet.colorado.edu. So the first question had to do with where these red dots were lining up. First off, this kind of wave is a longitudinal wave, also called a compressional wave because you have these spots where compressions, that's the red spots, they are lined up in compression. Sound waves from like a speaker, if you do this lab live through the simulator, the actual yellow part of the speaker moves forward and backward, compressing the air particles and making compression. So these red dots are in compressions. If you watch the video tutorial, it takes you through that also. In between the red dots, the parts that are spread out, these darker bands, those are called rarefactions. Way to remember that is it's rare to see particles in a rarefaction. So those red dots are most likely not going to be in rarefactions. They're going to line up in compressions. So the second question here is about rarefactions. Again, this kind of wave is called a longitudinal wave. Longitudinal wave. When you actually listen to this type of wave and change the frequency slider over here, you do this through the PhET simulation. You want to play with it some more. A higher frequency wave is going to be a higher pitch, a higher note, a higher tone. So those go together. Those are directly related. Higher frequency, higher pitch. Again, a lower frequency then, if this is directly related, the lower the frequency, the lower the tone, lower the pitch in this particular application on PhET. And again, when you're listening, you can also slide the amplitude up and down. So the amplitude slider allows you to go from 0 to max. Amplitude, although it's the height of a wave for a transverse wave, for a longitudinal wave like a sound wave, it's going to be how intense, how much energy is put into the wave. For a sound wave, that means loudness. Okay, higher amplitude, louder. A lower amplitude, like this question's asking about, is a soft sound. Next question asks about a low amplitude sound again, and that was kind of a mistake on the Google form to be redone and fixed for the next Google form you guys fill out. It'll be a higher amplitude, it'll be louder sound. Okay, max amplitude wave, that's going to be a loud noise. Then we go back to some of these waves here about just frequency in general. What's a higher frequency? A, B, C, or D. Frequency is how frequent or how often the wave shows up. An easy way to look at this is slide the mouse from right to left. The more often the wave shows up, the higher the frequency. So that means choice B right now is the highest frequency. And that's the correct choice here. Choice B is the highest frequency wave shown. What's the shortest wavelength? Just the opposite, the lowest amount of times that a wave shows up. That choice A is the lowest frequency. Now, it also happens to be the lowest amplitude. That's not what we're talking about here. This one and that one are actually pretty similar in amplitude, so that'll be fixed for the next one also. Wave A, wave C. If you chose wave C, I'll correct that in the grading. The last thing I want to show you, and hopefully this will work out, is showing you for credit for sound problems 1. Got a lot of questions over Remind about these questions on sound problems. I can take you through them. Sound wave produced by 400 meters away, it's heard 1.9 seconds later. What speed does the wave travel? This first question is really about velocity v equals d divided by t. That's 400 meters distance, okay, and that's 1.9 seconds. So it should be 400 divided by 1.9, and that's a 210.5, and there's going to be some digits here that I'm going to allow for 210.526 is what it should be, but I'll really accept anything between 210, 211 meters per second. Now for this one here, what has a frequency of 420 hertz, what's the period? The correct equation to use there is period, capital T, is equal to 1 divided by 420. So if you do that in the calculator, 1 divided by 420, you get 0.00238 seconds. And some kind of variation of this will be on the quiz or assessment for this, this unit. Frequency sound wave has a wavelength of 0.21 meters and a speed of 315 meters per second. So this is going to be a little variation here where we have velocity v, 315, is equal to frequency f times wavelength, that's 0.21. So solve for that, it's going to be 315 divided by 0.21, and you get 1500. That's 1500 hertz. This is going to be a long answer text, so I didn't include a answer key to grade this, but I'm looking at your answers instead. So if you're at a concert, the speed of sound wave is the same regardless of the wavelength, because the speed of sound has to do with the medium. How do you know this at a concert? If we were allowed to go outside and watch a concert, the bass notes that come from a bass guitar are going to reach the listener, the viewers, the audience, the same time that a high note from a guitar, even though it's a higher pitch, it's a higher note, shorter wavelength, longer wavelength, the music still sounds good to us. So this is really a matter of listening to some music and appreciating that high notes, low notes, when you listen to them from a speaker, don't get to you any sooner just because they're going fast in terms of frequency, more vibrations per second, don't move through the air any faster. Really cool to think about that in like the real world. It makes music sound good. Speed of sound is 0.2 miles per second. If you hear thunder 10 seconds later, and now this question goes back to velocity v, 0.2 is equal to a distance, d, divided by a time in t, 10 seconds. There's going to be 0.2 equals d divided by 10. When you solve for that, it's going to be 0.2 times 10, and that's going to be 2. As in 2 miles away. Now for this form, we're not accepting any units, so if you put units, the form will initially mark that wrong. Score might look a little weird when I email this out, but it should be, the answer should be 2 miles. You guys should just type in the number 2 here. If you're going to a race and you're going to time the race and you look back at the starter's gun, should you start the stopwatch when you hear the gun or when you see the smoke? Hopefully you guys did a little bit of Googling and you did a little looking at the notes that I provided. The notes indicate that sound moves a lot slower than light. So seeing the smoke from the gun is going to be a better time to start the timer than hearing the gun go off, because the light will reach you hundreds of thousands of times faster, suffice to say, than the sound of the gun. So if you start your time watch, set your time on your watch by the sound of the noon whistle, and these two actually go together, the last question and this question, and it's 3,000 meters away. The correct time you hear your watch ahead or behind. So the first part of this is just to realize that your watch is going to be behind. How much behind has to be, again, look at your notes. And these notes are online. They're on my Google site. They're also on eClass. If they don't open on eClass, use the Google site. It's about 300 meters per second. And this is going to give you a distance of 3,000 meters. So what we're going to do is we're going to take that 3,000 meters and we're going to divide it by 300. And we're going to get that our watch will be roughly 10 seconds behind. So the best choice here is going to be 9. Okay, so your watch is 9 seconds behind. Again, this will be changed slightly so that this way I can quiz you, test you on this kind of information. Last couple of questions are increase, decrease, remain the same types of questions. So those should go pretty quick. If the pitch of sound increases, what happens to its frequency? Pitch and frequency are directly related. Pitch goes up, frequency goes up. Now for frequency and wavelength, those are inversely related. If frequency goes up, the wavelength has to go down. More often the wave is, the shorter the wave is. So pitch increases, wavelength decreases. If the pitch increases, what happens to the speed? I don't know if you want to say these are trick questions, but the speed is based on what the sound goes through. Pitch, more frequent, shorter waves don't go any faster or slower. This is going to remain the same unless we make the air something else other than air, or make it hotter or colder. Pitch isn't going to affect the speed. And then finally, if the pitch of sound increases, what happens to the amplitude? Well, it turns out that a higher frequency note, guitar, something like that, that's higher than a bass guitar, it's not going to be any louder just because it's a higher pitch. So again, this stays the same, remains the same. Amplitude doesn't go up unless you play louder. And the last question here, frequency of 261.6 hertz travels through water at 1435 meters per second. This is again V velocity, 1435, is equal to F, 261.6 hertz, times wavelength. Once you guys write that down, you can see that you can solve for wavelength by dividing. So it's going to be 1435 divided by 261.6, and you get 5.485 meters. Again, either the same question or something very similar will be used to assess your understanding of this. The Google form, or however I decide to quiz you or test you. So hopefully you guys got a lot out of this. Try and join me live. Check into that live meeting this afternoon. I'll send it out via Remind, give you guys a link that way. And I'll put that link on eClass also. Thanks so much, and hope you guys have a great spring break. Enjoy it.